Hi, I'm Jack, a software engineer from Google, one of the core developers of the PyTorch XLA. Today, I want to talk about the PyTorch XLA internals. I will give a brief overview of the project and walk you through the code example while explaining what happened under the scene. In the end, I will also show you some supported models and the performance number we gathered on TPU. The goal of the PyTorch XLA project is to leverage the high performance capability of the Cloud TPU offer while maintaining a dynamic PyTorch user experience. The project reached general availability in September 2020. It currently lives in GitHub under PyTorch/XLA. Here is an example of running a PyTorch model on XLA with minimum changes. I highlighted the XLA-related change in red. Note that model definition, data loader, optimizer, and training loop are mostly unchanged. You also need to add a mark step call at the end of each training loop. You can see on the right. It is the xm.markstep at the end. This is the barrier that helps the XLA compiler decide when to start building a graph. I will say more about it in the later slides. We encourage you to check out our Colabs notebook examples. I provided a short link on the bottom left. Before we talk about the PyTorch XLA, let's first define what XLA is. XLA is a compiler-based linear algebra execution engine. It targets CPU, GPU, and accelerators such as TPUs. PyTorch XLA is a layer between PyTorch and the XLA compiler, which converts PyTorch operation into corresponding XLA operations. XLA will take this input and generate the device-dependent programs. PyTorch provides APIs for out-of-tree backend extensions. PyTorch's native function.yaml file defines function prototype for different PyTorch operations that can be overridden. Backends like PyTorch XLA can implement these operations. The PyTorch XLA implementation of an op will be used if one of the input to the PyTorch op is an XLA tensor. PyTorch XLA supports all PyTorch op by custom rolling or CPU fallback. So before we dive into detail of the PyTorch XLA core, I want to introduce you the lazy tensor system, which is a fundamental piece of the PyTorch XLA architecture. The lazy tensor system is built on top of the PyTorch Eagle runtime. Instead of dispatching each op individually to execute asynchronously, we record sequence of operation and build a direct acyclic graph. The graph will not be dispatched to the device for compilation and execution until the barrier is inserted or the value of the tensor is needed. The barrier here is the markstep API call we need to add at the end of each training loop. So with this in mind, let's go through a small example and see what happened under the scene. Let's first talk about the PyTorch to PyTorch XLA interaction. PyTorch XLA stores PyTorch operation as intermediate representation, or IR, when PyTorch API is used. For the code example on the right, we created a constant tensor with two elements and set the device to be XLA device. PyTorch XLA will record this tensor as a node in the graph. We will then create a second tensor by calling torch.logsonexp API and use tensor1 as an input. The PyTorch XLA implementation of the logsonexp will be used, since tensor1 is an XLA tensor, and tensor2 will also be an XLA tensor with the same device. PyTorch XLA will create a logsonexp node with 3 input and 1 output, which is a tensor2. This goes on when we create a third tensor by multiplying the second tensor by a constant. And now on the right, we need to return a value to print. This is when compilation happens. Zooming out now, This top circle represents whole IR graph at the moment when we encounter a barrier or need to return the value. This is when PyTorch XLA converts IR node to high-level optimizer HLOW text and pass it to the XLA compiler. Now here is the result. Note on the left, everything has been converted to the XLA ops. In this example, PyTorch op log_exp got converted to a sequence of XLA log, XLA reduce, and XLA exp. PyTorch op multiply got converted to XLA multiply. If we call markstep API instead of printing the value of the tensor, the same IR graph to HLOW text conversion will still happen. However, after the execution of the HLOW is done, PyTorch XLA will truncate each tensor's pending graph. This way, we can limit the graph size and are more likely to generate the same graph in each iteration. HLOW text generated will be fed to the XLA compiler. XLA compiler will perform numerous optimization, such as instruction fusion and algebraic simplification at the HLOW level. XLA will then lower the program into a machine instruction level IR for code generation. Compilation of a program can be expensive due to the optimization XLA performed. PyTorch XLA will casually compile a program and only perform the compilation when a new graph is encountered. PyTorch program will generate the same graph if the input shape, output shape, intermediate result shape, and operation used remain the same. Note that PyTorch program with a very dynamic nature will likely cause more recompilations. With that, we complete a full PyTorch XLA example walkthrough. We also have many official supported models with tutorials that you can try today. These models include Torch Vision's ResNet50, Fair-Seq Transformer, Fair-Seq Roberta, Hugging Face models, and Deep Learning Recommendation Model. Here is a chart of performance number we gathered by running Fair-Seq Roberta on different TPU devices. The TPU devices range from 8-core TPU v3-8 all the way to a 1024-core TPU v3-1024. You can see how well the PyTorch XLA model scaled up. Again, I want to encourage you to try out our Colab examples today and open GitHub issue under PyTorch/XLA repository. You can also check out our demo on Colab, Cloud TPU pod, and Fair-Seq. We'd love to hear what you think and how can we improve your experience with PyTorch XLA. That concludes today's talk. Thanks so much for watching. Hope you will enjoy using PyTorch XLA.